Okay, welcome back everybody. So here we're talking about section 3.5, which is derivatives of trigonometric functions. So first off, there's an important theorem, and if hopefully you recognize this. I made videos when we were learning limits, and I entitled the video Classic Limits. And so in that video, I actually proved that sine of x over x, the limit as x goes to 0, is 1. And I believe I also addressed this one, but you now have them as theorems. Okay, so make sure that you have these memorized. They pop up from time to time. And since the majority of this section is about derivatives, here I have written the 6 trig function derivatives. Now, your book goes through a few proofs of these. It uses the definition of a derivative to prove a couple of these. And I'm going to prove, which one was I going to prove for you? I'm going to prove the derivative of secant for you, okay? But, I would definitely commit these to memory, okay? These pop up, they will continue to pop up in Calc 1, Calc 2, Calc 3, differential equations, and so on. So make flashcards, commit these to memory for sure, okay? Okay, so let me verify that this guy is true right here. And then cosecant is very similar as far as the derivation of that. And then I'll let you read over the section, okay? So the section details the derivative of sine and cosine and tangent. Okay, so make sure you look over the section. Okay, but let's prove to ourselves that the derivative of secant really is secant times tangent. Okay, so the derivative of secant, well, we can write this as the derivative of 1 over cosine, because secant of x is equal to 1 over cosine of x. Then, we're assuming that we know the derivative of sine and cosine here. But here, I can use the quotient rule again. So we just talked about the quotient rule in the last section. So using the quotient rule, I would have the denominator times the derivative of the numerator is just 1, the derivative of any constant is 0, minus the numerator times the derivative of the denominator, all over the denominator squared. So simplifying that, cosine of x times 0 is 0. Minus 1 times minus sine x is a positive sine x. And we have that over cosine squared x. Now I can write this as 1 over cosine of x times sine x over cosine of x. And again, using some trig identities, 1 over cosine is secant, like we said. Sine over cosine is tangent. Okay, and so here we've shown that the derivative of secant is equal to secant times tangent. Okay, so, at the very least, if you don't want to memorize all of them, you can always memorize sine and cosine and their derivatives, and then you can derive the rest from there. Okay, let's do another problem here. Okay, so now we have another limit problem. So suppose we want to evaluate the limit as x goes to 0 of the sine of ax over the sine of bx. Okay, so limits like this pop up a lot. A couple sections ago, you actually graphically were going through limits like this. Now we're going to talk about it algebraically. How would you algebraically handle this? And for this, we really need that first theorem that occurred in section 3.5, that the limit as x goes to 0 of sine x over x is equal to 1. Okay, so as long as we have the argument of sine and the denominator of sine matching, okay, that limit is going to equal 1. And that's the key to doing limits like this. So, okay, if I were to multiply this original expression by ax over ax, look what I could do. Okay. So if I do that, and I rearrange things slightly, okay, so here notice that now I've rewritten it. All I've done is kind of rearrange the order a little bit. Now I have a sine of ax over ax times an ax over the sine of bx. So this guy here, this limit, because the argument of sine and the denominator match, it just equals 1. And so we're left with 1 times the limit as x goes to 0 of ax over the sine of bx. And now we do a similar process. So since I have a sine of bx, what if I multiply by bx over bx? Okay, and again, using the trick where I rewrite, I would have bx over the sine of bx times ax over bx. Now again, okay, this limit is also 1, which is kind of cool. Okay, so you could probably make an offshoot of this original theorem. The limit as x goes to 0 of x over sine x is also 1, which is neat. So that equals 1. And then we've got ax over bx. The x's can be canceled out. And so we really just have here the limit as x goes to 0 of a over b, which is just a over b. Okay, so you'll probably see quite a few of, these trig type limits, and most of them are based on the theorems. Okay, the original limit theorems in the very beginning of this section. Okay. All right, one more thing I wanted to go over, and that is finding y double prime. Okay, so hopefully, you've seen y double prime, you've read about it a little bit. We know how to find y prime. Y double prime is the second derivative. So you take one derivative, and then you take the derivative of the derivative to get y double prime. So here we want to find y double prime when y is equal to secant x times cosecant x. So we're going to have to use the product rule. Y prime is going to equal the first times the derivative of the second plus the second times the derivative of the first okay. So now we want to take a second derivative, but notice we have a triple product. So there's multiple ways to handle this. We could factor out a term, which might, I could factor out, let's see, a secant times a cosecant. And so then I would have maybe less products. It's debatable how you'd want to handle this. I guess what I would do is convert everything to sines and cosines. Actually, some nice things cancel, but what happens is we end up with powers of sines and cosines, and we don't know how to handle those until next week. So next week I'll revisit something like this. Okay? But for now, I think what I would do is I would factor out a secant and a cosecant, and then take the second derivative. And, maybe it'll be nice, maybe it won't. So y double prime, we're taking the derivative of the derivative. We have the first, I'm just going to treat this as one function for now. So we have the first times the derivative of the second. So the derivative of tangent, secant squared x. The derivative of cotangent is minus cosecant squared x. So minus minus gives us a plus. So we have the first times the derivative of the second plus the second times the derivative of the first, which is another product. So we have to use the product rule on the secant times cosecant. So I'd have secant times the derivative of cosecant, which is minus cosecant cotangent. We can see that. Plus cosecant times the derivative of secant, which is secant times tangent. Haven't gone off the board yet. Okay, so you can see there's a lot of terms to this. We could probably go about gathering some and seeing if anything cancels or simplifies and so forth. Okay, but I'll leave the simplification up to you guys. I wanted to illustrate the process of finding, a second derivative when you have more than one product, right? Okay, well that's all for this video. I will see you next in section 3.6.